A light ion beam is transferred to the entrance of the low-energy beam transport line, designed to accelerate ions to the energy level required for its injection into the linear accelerator. In the same transport line, there is a diagnostic device needed to tune the ion source, plus electrostatic magnetic lenses, which conforms the beam from the source to the linear accelerator entrance. The linear accelerator consists of two parts. The first part is an accelerator with a spatially homogeneous quadrupole focusing magnet, the full length of which amounts to 2.2 meters. It is made up of 4 sections, each feeding the 4-wire line. This accelerator was developed as a collaboration between the experts from the Institute for Theoretical and Experimental Physics and the Moscow Engineering Physics Institute. It was built in Snezhinsk. Over the previous 25 years of the post-Soviet development of the Russian acceleration school, it was one of the first accelerators of this type that was successfully created and has been placed into operation at our institute. The medium-energy transport line is located at the exit of the accelerator with a spatially homogeneous quadrupole focusing. This line has 2 doublets of quadrupole lenses, which conforms the transverse phase volume of the beam from the accelerator to a spatially homogeneous quadrupole focusing and the main accelerator, as well as an additional buncher that provides an increase in beam capture efficiency in the acceleration mode. The main accelerator is an Alvarez-type accelerator with quadrupole lens focusing. This accelerator type is sometimes referred to as the Alvarez-Blevett accelerator. It was created in the early 70s for proton and deuteron injection into the synchrophasotron. During the time of its existence, it underwent a rather long development period. A few modernizations of this accelerator have been carried out. Today it is capable of accelerating ions with about 1/3 charge-to-mass ratio. To date, it has been the principal injector of all the ions into the nucleotron. This accelerator is a 14.5 meters long copper resonator, the axis of which has a system of 52 drift tubes. Inside the tubes, there are quadrupole lenses performing beam focusing in transverse direction. Exiting the linear accelerator, the beam enters a transport line, which delivers it directly to the entrance of the nucleotron. The injection chain for light ions, unlike that used for heavy ions, is limited by 2 linear accelerators due to the fact that, in the nucleotron, fully stripped nuclei are accelerated and the vacuum conditions are sufficient for lossless acceleration. All the elements of the light ion injection chain are located in the existing hall of the linear accelerator LU20. In this picture, you can see the vacuum housing of the LU20 accelerator, the section with the spatial homogeneous quadrupole focusing, low-energy beam transport line, and the polarized ion source. This photo also shows the CO2 laser from the old laser source, which, to this day, has been used in the nucleotron runs. But in the nearest future, it will be replaced with a laser source based on a solid-state laser. The LU20 accelerator was built more than 30 years ago, and with respect to applied technologies, has become obsolete. Its vacuum volume is compacted with a rubber seal, and therefore it is impossible to achieve a super high vacuum in this accelerator. In terms of ion acceleration, it is not a very serious problem due to the fact that the beam travels only once. But that is a major challenge for the source, which must operate in a sufficient vacuum, and for the nucleotron, the entrance of which is fed with a gas flow from the linear accelerator. accelerator. That is why, in the nearest future, the LU20 accelerator is planned to be replaced with a more modern one, which will, firstly, provide a faster acceleration rate, and secondly, deliver better beam parameters.